In September 2015, scientists have been able to detect gravitational waves for the first time in history. Gravitational waves were first proposed by Henri Poincaré and Albert Einstein with his general theory of relativity more than a century ago. Gravitational waves are ripples in space-time generated by highly energetic events in the universe, such as binary star systems composed of black holes or neutron stars, and they propagate as waves supposedly in the speed of light, transporting energy and gravitational radiation. We still can't ensure they travel in the speed of light, but that's what scientists believe. These waves are constantly reaching Earth. However, as they come from a great distance from our planet, the effect caused by them is minuscule. They distort the space-time by 1 part in 10 to the 21, which is something like measuring the distance from here to our closest galaxy Andromeda with a precision of millimeters. So how is this possible? Well, scientists and engineers have created LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO is an L-shaped system with arms of 4 kilometers long. These arms are very long because LIGO works based on the principle of superposition of waves, which says that 2 or more waves traveling through the same medium at the same time pass through each other without being disturbed, and the net displacement of the medium is simply the sum of the individual wave displacements. So, to measure the stretching and squeezing of space-time, LIGO has a beam splitter which splits the beam from the source in 2 other beams which will travel perpendicularly in the direction of a very smooth reflective mirror and come back to the beam splitter and cancel each other out because of the perfect inverted superposition. However, if the space-time is distorted, one arm will become a little longer than the other, and in the next instant they will switch, continuing to do it over and over until the wave is passed. As the distances of mirrors change, the alignment of the waves also change, varying the superposition of valleys and peaks, no longer cancelling each other out when re-added together in the beam splitter. So that will cause a signal of laser light on the detector. In fact, to ensure the signal was not caused by a local agent on Earth, like earthquakes, LIGO has 2 systems in different locations, one in Livingston, Louisiana, and the other one in Hanford, Washington. The gravitational wave would pass through the detectors almost simultaneously, so they should obtain the same result. With the assurance of a gravitational wave detection, even though the shifting of the mirrors are only 1/3 of a wavelength, they can vary the intensity of the signal received on the detector. So by measuring this intensity, you can then measure gravitational waves. By the way, if we transform the signal of the gravitational wave into sound, we get something like this. The future of gravitational waves detection is tantalizing. Gravitational waves can bring a new horizon to astronomy and our knowledge about the cosmos. These waves could carry information about events still unknown in the universe, and hopefully it can also boost the studies on dark matter and dark energy, which constitute 95% of our universe. Hope you have enjoyed this video made for an elective discipline of my mechanical engineering degree. Thanks for your attention.